All right, so we're going to look at section 7.2 today, and that is going to deal with value using the disk method. All right. In fact, the next two sections are both going to deal with value, meaning, three-dimensional, how much can you fit inside this object? So basically, the idea is that we're going to create a 3D object by rotating an area created by a curve or created by some bounded region around a line. All right, so think about what we did in 7.1. We had this region. We're going to take this bounded region, and we found the area for it. If we rotate that around some line, that creates a third dimension, and that figure will have a certain value. So we want to find the value of that figure. Now, the general idea is to take that bounded region we had, look at cut cross-section. And when you rotate a rectangle around a line, that's going to create disks. And we take the limit of those disks, add them all up. As the widths go to 0, we get the actual value. Okay? Now, let me draw that on the board just so you can see that. Hopefully we got the board here. So let's pretend we have, this will be my y-axis, this will be my x-axis. And we have some sort of a curve. Let's say we make a region go hit the x-axis, and we rotate around the x-axis, okay? So if you rotate around the x-axis, we imagine this curve rotating around, we're going to get a three-dimensional object. It's going to have a side. Let me try to do this. Right? The other side of that thing is going to look like this. And it's going to be rotated around. Now, if this were a straight line, it would look like a cone. This is looks like some weird pottery vase, I guess. But it would come out from the board and rotate around. Okay? Now, if you think about what we did last time, we found the area of this section. Well, as that area rotates around, if we take into account the rotation, then that'll create value. Now, what's actually happening mathematically is that we're breaking up this area into a bunch of tiny rectangles. So there's a rectangle. And then each rectangle is going to be rotated around. When you rotate that rectangle around, what you're doing is you're creating a disk. And if you do that with lots and lots and lots of rectangles, then you can approximate the volume by adding up a bunch of disks. So we do the standard calculus thing where we let the widths of these disks get smaller and smaller and smaller, or the widths of these rectangles get smaller and smaller and smaller, and then add them up and take the limit of that summation. So that's what we're trying to do. We have limits of essentially disks made from rotating rectangles. And when you add that, all these disks up, you're ending up with the value, okay? Now, area of one of, not area, the volume of one of these disks. Well, how do we find the volume of one of these disks? Basically, you look at the radius of the disk, We'll call that R. And the height of the disk, well, I guess since we're laying it out this way, we'll call this the width of the disk. So width. And the total volume of this disk is going to be pi r squared times the width. Now, like I said, we're going to let these disks get thinner and thinner and thinner. In fact, we're going to let the limit of the width go to 0 and then add things up. So what's going to happen is this width, as you can see, since it's on the x-axis in the way I'm drawing it here, since the widths are going to be a change in x, when you add a bunch of those up, and take the limit as the change of x goes to 0, this change of x turns into a dx. And adding up infinitely many things is going to be converting to an integrating with respect to x. All right? So it's going to be basically like a pi r squared integrating with respect to x. Now I'm going to erase that because it's better written on my notes than it is on the board. Okay? So each disk has volume pi r squared times the width, or pi r squared times the height if you lay this out horizontally rather than vertically. You sum all the disks, and this becomes your formula to find the value. Notice this is what I just said. Pi r squared times dx. Integrated from some point, some x value of a to some other x value of b. Now, this formula would be given to you like on a cheat sheet or something, or you could write it down yourself if you're taking, oh, how do I say? You can look it up if you're doing your homework online. But that's the main idea. Now, obviously, I rotated my picture. In my picture, I rotated around the x-axis. If you rotate around a vertical axis, then you have to do everything with respect to y rather than with respect to x, because the change in those little widths of the disks are going to be y values rather than x values. Now it turns out not just the y-axis or the x-axis works with this rotation, but any horizontal axis you can do this way. Any horizontal axis, the width of that disk is going to be a change in x. And any vertical axis, the width of that disk is going to be a change in y. Now, you might see here that in my formula, I had a specified radius, which I called r. Here we have r of x. So my radius is a function of x. The reason that is because if I'm looking at this disk that I just drew here, it's going to have radius of, let's say, 3. But as I move over here, a disk over here may have radius of 4. So the radius depends on what value of x you're at. At this value of x, let's say x equals 0, the radius is that much. It increases for a while and then it decreases, and you can see again the radius of these disks are going to increase and decrease based on where we're at on the curve. So let's do an example of finding volume utilizing this disk method. So example 1 says, find the volume of the object made by revolving the region created by y equals 4 minus x squared, x equals 0, and y equals 0 in the first quadrant. So that's our region. And we're going to revolve that around the x-axis. Okay? So you can do this a number of ways. You can graph this. You can, I like to draw it by hand. Some people like to, use Desmos and graph it. Some people, just try to do it without graphing. I would say, in general, graphing it is a good way to do it. All right. So first step, look at what region we're talking about and how it's being rotated. When things get more and more complicated, it's more and more important that I know what we're doing. Or that we know what we're doing. So I'm going to graph this region. All right. So you can do this utilizing anything you want. I'm going to bring up Desmos. You know what? No, I apologize. I'm going to draw it on the board. Okay? That's so that I can do things on the board. So first one, y equals 4 minus x squared. If you graph this, again, I'll let this be the x and y axis. This is a parabola pointed down. I'm not real accurate on my drawing, but that's okay. All right, parabola pointed down, 4 minus x squared. This point up here is the point 0, 4. This is the point 2, 0. This is the point -2, 0. All right, that's the region, that's the first curve. The other two curves, one is the line x equals 0, that's the y-axis. And the other is the line y equals 0, that's the x-axis. So notice that creates two different bounded regions. But our example said that we're looking at the region in the first quadrant. And so we have two bounded regions. We're focusing in on this one because it's in the first quadrant. So I'll erase that other side. So that's the region we're going to look at. And we're going to rotate that around the x-axis. All right, I generally draw a little circle there with an arrow to remind myself where we're rotating it around. The other thing I do a lot of times is I will put a rectangle in here just so that I know how my rectangle is oriented, how the width is oriented. Because notice that by drawing my rectangle this way, I notice that the width of this rectangle is with respect to x. In other words, as it gets wider or more narrow, it's getting wider or more narrow in the x direction. That tells me the volume is going to be pi r squared, but everything's going to be done with respect to x. I'm rotating around a horizontal line, so everything is done with respect to x in the disk method. All right, so now I have to fill out some things. Well, this A and B since we're integrating with respect to x, have to be start and stop values on the x-axis. And if you think about where this region starts at, it starts at an x value of 0 and goes all the way over until you hit an x value of 2. So the value is going to be pi, integrate from 0 to 2, some radius squared. So the bounds are going to go from 0 to 2 because our x values went from 0 to 2, and we were integrating with respect to x. Now, what about the radius? Well, if you think about rotating this and creating a disk, what that rectangle is, well, it'll have a, I call it a ghost image. Once you rotate it, it's going to have a mirror image on the other side. But notice the size of the disk that we're creating. The size of the disk is going to be, well, the diameter is going to be twice the length of the rectangle, which means that the radius of the disk is exactly the length of this rectangle, right? So the radius of the disk is going to be the same as the length of the rectangle. Well, how far is the length of the rectangle? Well, the rectangle goes from this top curve, y equals 4 minus x squared, down to the x-axis, y equals 0. So I'll write that we're going from y equals 4 minus x squared to y equals 0. So my radius is the distance between these two curves, which in this case is 4 minus x squared down to 0. And that's it. Obviously, in this case, down to 0, subtracting 0 isn't going to do anything. So it's basically just 4 minus x squared, quantity squared. But the reason why it's because, again, the length of this rectangle. Rectangle starts at the top of the curve, goes down to the bottom of the curve. By the way, when I say this rectangle is just one example of all of the rectangles that we're going to draw, right? So if the one I drew was over here, it'd be a lot shorter. If the one I drew was over here, it'd be taller, right? In fact, we're going to draw infinitely many rectangles, theoretically. I'm not going to draw them, but theoretically, we're going to have infinitely many rectangles within this range. Now, at this point, it's time to turn to your calculator. So we're going to turn to your calculator and go ahead and do that. What I've done, I've come into class today so I could write in the board and also utilize the camera here. So this time I am going to show how to integrate utilizing your TI-84. Let me zoom in a little bit. There we go. Now I am going to do something. Settings. Okay. So, remember I said this in the last video, math, number 9, can't see that, is function integrate. So you can either scroll down to number 9 or you can just press the number 9 on your calculator. And my calculator has math print on, so it looks like this. Oh, I forgot to insert. I should insert a pi before that, right? So second insert, and then the pi. I apologize. So we're going to go from 0 to 2. We're going to take 4 minus x squared. Oops. 4 minus x squared. And then square that. If you wanted to include the minus 0, you could. 4 minus x squared minus 0, quantity squared, right? That's fine as well. You'll get the same thing. And we're going to integrate with respect to x. Make sure that when you're typing in x, you're utilizing the variable key for x, and you're not utilizing the alpha x. So you're using the variable key right here. Then hit enter. And sure enough, it's about 53.62. So if you wanted the answer rounded to 2 decimal places, it's about 53.62. However, WebAssign may ask you also to give an exact answer. And what the exact answer is the answer without, or I should say, with pi not being calculated in. So you can simply just say divide your answer by pi, and notice that's 17.06. That's going to be 17 and 1/15. Okay. All right, I had it come up as an improper fraction, but it's 17 and 1/15, or 256 over 15 pi. So if you write your answer, again, there's a lot of different ways to write it, but 256 over 15 pi, or 17 and 1/15 times pi. Okay, either way is perfectly all right. So that's the idea. Okay, that's the main idea of this section. Okay, we're going to get a little bit more in depth as we go along, but that's the big concept. All right, let's do another one. This time, instead of rotating the region around the x-axis, let's change it up and rotate this same region around the y-axis. Now, because we rotate it around a different axis, we are going to get a different answer as far as volume goes. We're not going to have the same volume because it's not going to be the same object, right? If you take a circle and rotate it one way, you can get a sphere. If you rotate it a different way, you can get a tube, right? So these types of things are highly dependent upon how we rotate it. So we should not expect the same volume by rotating things around the x-axis as we do when we rotate the things around the y-axis. So let's go ahead and do this one. Excuse me, this is, push pause just for a second. All right, so here we go. A little bit high there, but that's okay, a little bit. So y equals 4 minus x squared. We already know the region, so I'm going to draw it pretty quickly. It looks like that. That's the bounded region. those are the points of interest. We're going to rotate this around the y-axis. Now, if you do that, in order to create a disk, you're going to have to draw your rectangle this way. All right? All those rectangles, those infinitely many rectangles, you're going to have to draw that way. And you're going to create a bunch of disks that are all flat, right? That are all horizontal shape. So because I have the rectangles drawn this way, the width of those rectangles is going to be done with respect to x. It's going to be, as you get a wider rectangle, your change in x is going to be higher. As you get more and more narrow, your change in x is getting lower in the y direction. So the volume on this is going to be pi integrate CD, radius with respect to y squared, and integrating with respect to y. So that's the value, or that's the formula that we're going to use in this case. So when you do things with respect to y, when we do things with respect to y, my bounds have to be y values. This is saying, where do you start at in the y sense, and where do you end at in the y sense? So as my rectangles go, we're going to start down here at the y value of 0. And we're going to move up until we hit the y value of 4. So we're going to be integrating from the y value of 0 to the y value of 4. Again, I have to do y values because we're doing integrating with respect to y. Now that also means this function here has to be written with respect to y. My function y equals 4 minus x squared is not written with respect to y. This is y is equal to a function of x. We want x is equal to a function of y. So essentially, I want to solve this for x. If you add x squared to both sides, and then subtract y, you get x squared equals 4 minus y. Now you can take the square root of both sides, and since we're in the first quadrant, I can use the positive square root when I take a square root, all right? If we were in the second or third quadrant or fourth quadrant, we'd have to be really careful about that. But since you're in the first quadrant, we can take a positive square root. All of our x values, again, right from here to here, all of my x and y values are both positive, right? First quadrant. So when you take a square root, you get x is equal to 4 minus y underneath the square root. So x equals the square root of 4 minus y. And now I have my function written with respect to y. Now, that's just this part of the rectangle. That's just the right-hand side of the rectangle. The other side of the rectangle is the line x equals 0. It's the y-axis. The y-axis is the line x equals 0. So we're going from x equals square root of 4 minus y to x equals 0. That means the radius, which again is just the length of the rectangle itself, is square root 4 minus y down to 0. And then we're going to square that radius with respect to y. Integrate with respect to y. Again, if you want to leave off the minus 0 when you type it into your calculator, by all means go ahead. But that's the idea. All right? Okay. So let's type that into our calculator. Kind of dirty screen. I'm going to have to clean that off. All right, so let's type that into our calculator. Let's take pi math 9, integrate 0 to 4. Now here's where it gets a little bit tricky. Obviously, I do not have a y variable. When I click this variable key, the only letter that we can use is x. I hope it's not too much of a pain to just switch up using the letter x versus using the letter y when you integrate. So again, you can't use a letter y. You can't go alpha y. That won't make sense to your calculator. So you have to use whatever variable the calculator gives you. And the calculator doesn't care whether this is an x or a y or an r or a theta or whatever. You can just do it that way. So you get 25.13, so on and so forth. If you want to get the exact answer, that's 8 pi. So that's the deal. This value we just found out was exactly equal to 8 pi, which is approximately 25.13. Again, you just have to use the letter, the only letter that your calculator can deal with in this mode, in the normal mode, is y. Obviously, if you go into polar, it can use the letter r, et cetera, et cetera. Or t, I'm sorry, theta, I think. All right. Hopefully that makes sense. Okay. Now, I want you to try this problem on your own. Push pause on the video if you're watching at home, because I'm not going to take a whole lot of time. But push pause on the video if you're watching at home. Obviously, if you're in class, you can just keep going. All right? So I'll wait about 5 seconds and then go do the problem myself. Okay, so we're revolving the region created by 2 minus x squared, or excuse me, y equals 2 minus x squared, and g of x equals 1. That's also known as y equals 1. Around the line, y equals 1. So this time, we're not revolving around an axis. We're revolving around a horizontal line, but one that's not the x-axis. So if you start to draw this, y equals 2 minus x squared, that's a parabola pointed down. Let's pretend this is the y-axis, this is the x-axis. So it's a parabola pointed down. Okay? Very similar to our last problem. And the line g of x equals 1, or the line y equals 1, is a horizontal line right there. Now, notice this does not say just in the first quadrant. This says the entire region is bounded by these two curves. So what we're looking at here is the bounded region right there. Okay. We're going to revolve around the line y equals 1. So we're going to revolve this thing around y equals 1, which is nice because it touches y equals 1. We're getting something that looks like this. Almost spherical shaped, but has little corners on it. All right. All right, so if I'm revolving around this line and I'm wanting to create discs, my rectangles have to go in this direction. They have to be vertical, which means width of the rectangles, I'm going to have to end up integrating with respect to x to get the value using the disc method. So value is going to be, again, pi, integrate from a to b, radius squared with respect to x. And everything's with respect to x because width of the rectangles has to get smaller and smaller and smaller in the x direction. Okay. All right, let's first take care of these bounds. If you actually look at where these 2 points are, the left-hand most point is -1, 1. Again, when in doubt, just use your graphing calculator to find the intersection points. The right-hand most point is +1, 1. This point up here is 0, 2. Again, you can see this sometimes gets fairly messy looking. Nice to have an eraser. So as far as x values go, we're going to go from -1 to +1. Now here's the radius. The radius is the length of this rectangle. Again, it's the length of this rectangle because we're going to rotate it around. That means the diameter is going to be from the red top to the green bottom, but the radius is going to go from the red top to the red middle, or this line here. So if you notice, the radius is going from y equals 2 minus x squared, that's the top, to y equals 0. Or excuse me, not y equals 0. In this case, y equals 1. Everybody get that? Since we're revolving around the line y equals 1, goes from the top of the curve down to y equals 1. So that's what we're going to do. The radius is going to be that difference. 2 minus x squared down to 1. and then you square the whole thing. Be careful how you type that in. It's got a little bit of a glare, but this is 2 minus x squared minus 1, and then the whole thing has to be squared. So be really careful how you type that in. Oh. So pi, once you start getting used to this, it goes quicker and quicker and quicker. -1 to 1. And then start your parentheses, 2 minus x squared minus 1. And then that whole thing's going to be squared. Don't forget, you have to tell the calculator that you're integrating with respect to x. If you divide by the number pi, notice you get 1 and 1/15. So you can call this 1 and 1/15 times pi, or you can call this about 3.35. So there you go, 3.35. I'll emphasize that decimal there. So either way you do that, that's how we get it. All right? Hopefully that all makes sense. Hopefully that all makes sense. That's the idea of the disk method. Now, we've seen rotating around a horizontal axis, like the x-axis. We've seen rotating around a vertical axis, that's the y-axis. The other curveball, we can rotate around something that's not an axis, like y = 1. We did that in example 3. But an interesting twist comes up when I have space in between. If you go back to examples 1, 2, and 3, all of those turned out to be solid objects. So there was nothing that it was a completely solid object. So the volume was just this nice solid figure. We can do it with one integration. It turns out when we have space in between, we can do those with 2 integrations. Or at least many times we can do those with 2 integrations. So this says find the volume of the object made by taking this region around revolving this region around the x-axis. The region is created by y = square root of x and y = x squared. All right. So, like usual, I'm going to start by drawing this. If this is the y-axis and this is the x-axis, the square root of x does this, and x squared does this. So the bounded region that these two create is this one in here. All right, it's this little, I don't even know what to call that, weird shape. Now, we're going to take that region, and it says, take this region and revolve it around the x-axis. That's going to give me an image on the other side that looks like that. Now, by the way, this is not, when we actually revolve it, we get a solid thing that revolves around. In other words, this is going to be like a tube shape, but I'm going to be able to stick my finger in the middle of this. In other words, this is creating some sort of a circular bowl pattern, where this is the outside of the bowl and the inside of the bowl is hollow. All right? So you could stick your hand in there and, this thing would rotate all the way around. Hopefully that makes sense, what the object is we're figuring out the volume of. So you can stick your hand in, rotate it around, you get a bowl shape, like you eat out of a cereal bowl. And this is basically the volume of a cereal bowl or something like that. Obviously, a cereal bowl doesn't have edges that look like this, but you get the point. Now, this creates an issue because when I try to do a disk method, the rectangle that I want to rotate does not go all the way down to the line I want to rotate it. In other words, when we take this rectangle that we want to rotate around, what's happening is we're creating sort of like a disc, but with a hole in the middle. I didn't draw that very well. That's okay. We're creating a washer. So oftentimes, when you have space in the middle, when your rectangle that you really want to rotate on your region doesn't go all the way down to the line we're rotating it around, the technique here is often called the washer method. Now, it's called the washer method because, again, it looks like a washer. But really, if you think about what a washer is, it's a disc, it's a big disc with a disc cut out of the middle. So a washer is simply a disc minus another disc. And that's how we're going to treat it formula-wise. We're going to say, well, let's pretend we want this washer. How I can do that is I can find the volume of the bigger disc and then subtract out the volume of the smaller disc. Okay? So that's what the formula is going to do. Now, how do we figure out the bigger disc, the smaller disc? Well, the bigger disc is just the top curve all the way down to where we're rotating. And the smaller disc is the bottom curve to all the way down where we're rotating. I'll draw it like that for now. So that's what we have to do. We have to do two disc methods and then subtract them. Now that might seem like a lot of work, but the calculator does it really quickly once we get it set up. So let's take this example. All right, let me start filling in some things. First off, this point over here is the point 0, 0. This point over here is the point 1, 1. So when we want to do the volume utilizing a disk method, or I should say the washer method, disk minus disk, what we're going to do is we're going to go pi radius squared minus pi integrate a different radius squared. And traditionally, people call the one that's bigger, this, the capital R radius, and the one that's smaller, they'll call this lower r. So uppercase, lowercase, they'll use. Again, that's what most people do. All right, so let's fill this thing out. Obviously, both of these are going to be integrated from 0 to 1 because that's we want to match those things up. So we're going to integrate from 0 to 1, the bigger radius, minus integrate 0 to 1, the smaller radius. Again, squared. Okay, so I look at this larger of the two rectangles. The larger of the two rectangles has a top at y equals square root of x and has a bottom at y equals 0. So the larger of the two rectangles goes from y equals square root of x to y equals 0. That's the larger of the two rectangles. So here, square root of x minus 0 squared. The smaller rectangle, the one that I've filled in as solid, is from y equals x squared, that's this curve here, down to y equals 0. So x squared minus 0, square that radius, and there we go. Now, if you read along in the book, technically you can combine these into one big integration if you'd like. Since we have the same bounds and we have pi in front of both, we could, if you'd like, combine these into one big integration. Your book does this. It writes this as integrate from 0 to 1, square root of x minus 0 squared, minus x squared minus 0 squared dx. So it does that. But I think it's just as easy to plug it in this way into a calculator. So this is the way I tend to do things. So I tend to do things just like that. So that's what I'm going to do right now. Plug it into my calculator, get an answer. So here we go. Pi, integrate from 0 to 1, x, square root of x minus 0, quantity squared, respect to x, and then I do minus, math 9, there we go. So hopefully everybody sees how I'm doing that. I'm doing it all in one line. You could also do it in 2 lines if you'd like. You could calculate that integration, calculate that integration, and then subtract them. So if you want to do this in a 2-step process, by all means, go ahead and do that. All right, I got 0.9424. If you think about what that is as an exact answer, that's 0.3 times pi. So 0.3 times pi, or about 0.94. Okay. So that's the idea. And by the way, usually WebAssign wants you to answer things like this. When we take the test, our test will be through Moodle. We'll use 0.94. So on the test, a lot of times I have this is the answer, like a decimal rounded to 2 places. Okay, so on Moodle, usually decimal rounded to 2 places. A lot of times in online homework systems, you have to write exact answers. Okay. So that's about, that is all the concepts in this section. We're going to do some more examples and how to do things, but basically it's rotating around curves. We know how to do whether to pick rotating with respect or finding value with respect to x versus y. We know how to use different rotating around things that aren't the x or y axis. Now we know how to deal with space in between. So essentially, we have all of the tools we need to be successful in this section. Okay? So I'm going to pause this video and we'll start on in the next video with some new material.